Hi everyone, welcome to our second video on the introduction to vectors. The next topic is on the distance between two vectors, which may seem like a funny thing to define because since all vectors start at the point 0, 0 or 0, 0, 0, shouldn't the distance between them be 0 as well since they're all touching? No, we're going to get around that by defining the distance to be the distance between their endpoints, which could be non-zero. We'll define this distance between endpoints using Pythagorean theorem. So the formula is that the distance between the vector u and the vector v is given by the square root of the difference in the x components, all squared, plus the difference in the y components, all squared. So if the vector u has components v, the vector u has components u1, u2, and the vector v has components v1, v2, then that's what this formula would correspond to. In 3D, we'll also have a z part. So we'll have the v1 minus u1 squared plus v2 minus u2 squared, so the x part, the y part, and then the z part, the z component of the vector minus the z component of the other vector, all squared. You can play around with this formula and convince yourself that the order in which you do the subtraction does not matter. What that means is that the distance between u and v is the same as the distance between v and u, which makes sense. So let's use this formula for an example in R2. Find the distance between the vector u, 4, 5, and the vector v, negative 1, 5. So our distance between u and v is equal to the square root of the x minus the x. So and remember, it doesn't matter which one you subtract from which one. So I'm going to do the first one minus the second one, even though the formula said second minus first. If you want to do the other way, you can. It won't make any difference in our final answer. So x component minus x component, all squared. We're subtracting a negative, so we're going to have to be careful with that. Plus y component minus y component, 5 minus 5, all squared. Okay, let's simplify. 4 subtract negative 1 is the same as 4 plus 1. So square root of 5, all squared. 5 minus 5, we have 0, all squared, and we'll simplify that. So the square root of 25 plus 0. So that's the square root of 25, which is 5. So if you had graph paper and you were to draw these two vectors very carefully, 4, 5 and negative 1, 5, and then use a ruler, draw the straight line between them, measure that distance, you'd see that that distance is 5 on your graph paper. Okay, another one, this time in 3D. When we want to find the distance between this vector u, 4, 5, 7, and the vector v, negative 1, 5, 3. So distance between u and v. This time I'm going to do the other order of subtraction just to show you it's arbitrary, for this particular formula at least. So u will have this part squared plus the next part squared plus the next part squared. Okay, so we'll have 4 minus, I said I was going to do the, I was going to reverse it, so we'll reverse it, minus 1 minus 4, and then we have 5 minus 5, and then 3 minus 7. Okay, let's simplify. This time it's negative 5 all squared plus 0 all squared plus negative 4 all squared. Negative 5 squared means negative 5 times negative 5. The negatives cancel, we get positive, so square root 25 plus 0 plus positive 16, negative 4 times 4. Now we can add all the pieces together. 25 plus 0 plus 16. So square root 41, and that's it. 41 does not square root. That's the best we can do. That's our answer. It's not a very good square root though. That's not the best I could do. I have to redraw the square root symbol. That's a little better. And it's okay if the distance comes out with a square root. It's okay if the distance comes out with a fraction, if the inputs have fractions in them. What's not okay is that the distance come out negative. It should always come out positive. Okay, length. The length of a vector is connected, or the formula for the length of a vector is connected to the formula for the distance of a vector. We could say that the length of a vector is the distance between the vector of interest and the zero vector. There's different names that we attach to the length of a vector. One of them is magnitude, another one is norm. And there's more than that. They all mean the same thing. So you could be asking the question, find the norm of V. Find the magnitude of V. It also has this double bar notation, which looks a little bit like absolute values, and it's easy to get confused. We'll say that the length or magnitude or norm of a vector is denoted by double bar, vector, and double bar. If you want to recycle that previous formula that we had, it'd be equal to the distance between the zero vector. That's a zero that's bolded. Notice you can't tell it's bolded, so I'm going to put an arrow above it. The zero vector and the vector v. So you have v1 minus 0 squared plus v2 minus 0 all squared. Subtracting 0 doesn't change the v1 and the v2, so we can just put v1 and v2. And that is directly Pythagorean theorem. Shown on the bottom is just a diagram reminding you of what Pythagorean theorem refers to. If you have a right angle triangle, one side v1, then another side v2, the sum of the squares of those components, subsequently square rooted, gives you the length of the hypotenuse. And that's what we're using for our distance. In 3D, it just has the z component squared tacked onto the end. It's important to not take the square root until you have all the components added and squared. Well, squared and then added, and finally doing the square root, so don't try to skip steps. So first example for doing length, we'll find the length of this vector v, 2, 3. I'll put the arrow above it because it really should be there. So I'll use this fancy notation. Double bar v equals the square root of the x component squared plus the y component squared. So the square root of 4 plus 9 square root 13. And that's all we can do. Okay. We have a special name for vectors that have a length of 1. We call that type of vector a unit vector. Now, length is defined in that way that we just described, the square root of the sum of the square of the components. It's not defined by adding the components all together. So in this example, we'll see that it really highlights this definition. Which of the following vectors, u or v, is a unit vector? So u is 1/2, 1/2. 1/2 plus 1/2 is 1, so it might be tempting to say that one's a unit vector. Or v, 4/5, 3/5. You add those together, you don't get 1, you get 7/5, which are larger than 1, so you might think, well, that can't be a unit vector. But let's go by the definitions. Let's use the definition of each. So we're going to find the length of u, and then we'll find the length of v. And we'll see which one gives us 1. So the length of u, we have the square root of 1/2 all squared plus 1/2 all squared, which is the square root of 1/2 multiplied by 1/2 I'll write this one out as a reminder of how fractions work. It's the first fraction we've talked about, I think. And another 1/2 plus 1/2. 1/2 times 1/2, I mean. Well, 1/2 times 1/2, we do top times top, 1 times 1 is 1, and then bottom times bottom, 2 times 2 is 4, so 1/4 plus, and the same thing for the next piece, 1/4. So that's the square root of 2/4. 2/4 simplifies, square root of 1/2. And that's definitely not 1. Square root of 1/2 is not equal to 1, so it's not a unit vector. It does not have length 1. Now let's check vector v. So its length, or norm, is 4/5 all squared plus 3/5 all square rooted. We'll follow the template that's above. 4/5 squared means 4/5 times 4/5, top times top, 4 times 4, 16, over 5 times 5, 25, plus top times top, so 3 times 3, 9, over 5 times 5, 25. They already have common denominators, so we can add the numerators together. So we get square root of 16 plus 9 over 25. So square root of 25 over 25, which is the square root of 1, which is 1. Since 1 times 1 is 1. So this is a unit vector. V is a unit vector. Next question is your first curveball. These are typical problems inside math courses, and including inside this course. You're asked to find the value of a parameter that makes something happen. Find the value of k such that the derivative is 0 at this point, if you're taking a calculus class, or find the value of a such that something else happens. So you're looking for a way to meet a target condition. In this question, the target condition works as follows. We have a vector u given by 1/3, comma, negative 2/3, comma, k. So it's a 3D vector. We're told it's a unit vector. And based on the information, we're asked what must be the value of k. So, is a unit vector. This part means that the length of u equals 1. Let's find the length of the vector. So the square root, we need more space, of 1/3 squared plus negative 2/3 squared plus k squared must be equal to 1. Okay, next thing I'm going to do is simplify the inside. So 1/3 squared is 1/3 times 1/3. So 1 times 1 on top, which is 1. 3 times 3 on the bottom, 9. So 1/9 plus negative 2 times negative 2, positive 4. 3 times 3, 9. Plus k squared equals 1. Now I'm going to make common denominators inside there. I already have common denominators for the first two. I'll just add those together. So 1/9 plus 4/9 is 5/9. So square root of 5/9 plus k squared is equal to 1. The next thing I'm going to do is I'm going to square both sides. And note that the square root of something, all squared, is just equal to that thing. Squaring something gets rid of square roots. That's why we're doing it. We want to make that square root disappear. So we have 5 over 9 plus k squared is equal to 1 squared. 1 squared being 1 times 1, which is 1. So 5 over 9 plus k squared is equal to 1. Now, the goal is to get k. So I'm going to continue isolating for it. By subtracting 5 over 9 from both sides. So k squared is equal to 1 minus 5 over 9. Next step. We can take the root of both sides at this point, but it's better to simplify the right-hand side first. To do that, I'm going to make common denominators. That 1 is really a 1 divided by 1. I'm going to multiply top and bottom by 9. So k squared is equal to 9 over 9 minus 5 over 9. Another way to think about this is I've replaced the 1 with a 9 over 9, which is 1. Same thing top and bottom. Now I can subtract the tops because the denominators are the same. So k squared is equal to 9 minus 5 over 9. So k squared is equal to 4 over 9. And then what squared gives you 4 over 9? Well, k could be 2 over 3, or k equals negative 2 over 3. So we get two answers. Also, can be phrased as k equals plus or minus 2 over 3. So that plus minus symbol means that both of these solutions are contained, the positive and the negative. Okay, and we'll continue with more vector operations and vector properties in the next video.